So hello everyone. In this video, we are going to cover the motion graphs in different scenarios and what they represent, how to determine and various quantities using those graphs. Okay. So we have already covered some basics about uh, kinematics in this previous videos. Now we are going to start with motion graphs. Now in motion graph, we want to explore first what does different quantities of the graph represent. So we will make a table first. And in this table, there are two quantities that we can figure out from a graph. One is the gradient of the graph, gradient or slope of the graph, you can say. And other is area under the curve. So when we have this table, it is easier for us to remember what different quantities we can find from the graph. So we will see different graphs, like for example, if I have a distance versus time graph, a displacement versus time graph, then we have speed versus time graph, a velocity versus time graph, and acceleration versus time graph. So what are those quantities? So gradient of distance versus time graph will give you speed, while area under the curve gives you nothing. Similarly, displacement versus time graph will give you velocity, and the area under the curve gives you nothing. If I have speed versus time graph, the gradient would have given me acceleration, and specifically only the magnitude of this acceleration, and the area under the curve gives us distance traveled. And for the velocity versus time graph, it is also acceleration, but it will both have direction and the magnitude. While for the area under the curve, it is change in displacement. Acceleration versus time graph. The gradient won't represent anything, but the area under the curve will give you change in velocity. So these are the basic things that we will like to cover here. Next, we are going to talk about is how these quantities like shape the graph in different scenarios. So if I let me draw one speed versus or distance versus time graph, and then we will look at different scenarios in that graph. So I will first start with the distance versus time graph. So in a distance versus time graph, first thing, every distance traveled is a positive quantity, so there is no negative axis required in this. So for example, if the motion is like this, okay, let this line be A. So A represents the object is stationary. So there is no motion, there is no change in velocity. Then if I have graph like this, let it be B, it represents a constant speed. Similarly, if I have two graphs which are very much similar to each other, like this starting from origin, so C is a constant speed, but since it has a lower gradient, the speed at C is less than speed at B as it has lower gradient. Now, we have one more example of this graph. Imagine the graph is changing like this. Let this be D. Now, D represents there is an increasing gradient. And whenever there is an increasing gradient, it represents increasing speed. And if it is increasing speed, it will represent a positive acceleration. Okay. And similarly, similar looking curve can be something like this, where the velocity or the speed is decreasing, the curve is getting more and more horizontal. So it is a decreasing gradient, and thus it represents decreasing speed. And thus we can say it is a deceleration. Okay, so these are the different scenarios that are possible. Now, what are the different cases for a displacement versus time graph? Is it exactly similar to distance versus time graph? Let's see. So I will need a positive and negative axis both here. So this is a displacement versus time graph. So the first scenario I will like to draw is the same A, that is object is stationary. And then let's say we have something like this, where the graph has a gradient. So the B represents a constant velocity. Okay. Here, there is one more graph that is possible. Let's say I have an object which has velocity like this. But what does this represent? It represents, again, if it is linear, it will be a constant velocity, but in negative direction or opposite direction. Okay. Then we have our curve that gradient is increasing upwards. Okay, and curve that has decreasing gradient. Okay, so this can be D or E. So D represents, like in a previous case, the gradient is increasing, so it represents increasing speed or velocity, and we can say increasing velocity, and it can be a positive acceleration. Okay. Similarly, if we have E, we will have a decreasing velocity or a negative acceleration or a deceleration, let's say. Now, what is unique about this graph? One more thing that is possible here, that it can be something like this. It starts from a certain displacement and then it goes in the opposite direction completely, something like this. Okay, so it is same as, if this is F, it is same as C. It is just that it has a different starting point. Okay, so it has the same as E, but with different starting point or starting position. Okay, so these are the two cases of those graphs. Now, what else we have? Imagine if same scenarios can be redrawn for the speed versus time graph. So here, if we have a graph, again, it will be only replicate a positive side. So speed is a scalar quantity. So we have speed versus time graph here, and I will draw multiple examples of this. So if this is the case, let this be A. So A represents object is stationary. But if I draw a B like this, the object is moving at constant speed. Okay, so acceleration is 0 in this case. Then if we have something like this, that will represent something that is increasing speed at a constant rate. So we can say that constant positive acceleration. Okay. Similarly, you can have something like this, which can cause speed from a certain point to come to 0. Let this be D. So D represents constant negative gradient or negative acceleration. Okay. So these are the scenarios that are possible here. Now, one more scenario that is possible is that the curve might be going upwards. Whenever the curve goes upwards, it is an indication that the acceleration is increasing. So E is the acceleration is increasing. Okay. That will be E. Once we have learned through this, we can replicate this information into a velocity versus time graph. Now, in velocity versus time graph, we can have both positive and negative. So the first part here is the same as A and B. So if this is like A, here A will represent constant speed. Okay. Then we can have something like this. Let there be point X. So this B represents that in a constant acceleration, a constant gradient in a constant acceleration. Okay. So in a constant acceleration, the gradient is same. Okay. The velocity first decreases and goes back to zero. This velocity decreases. Okay. And then it increases in opposite direction. Okay. Like this, there can be many more points, but these are the important ones. If we have certain curve which looks like this. Okay. So let this be C. So what does C represent? C represents a decreasing gradient curve. And decreasing gradient is very much common. It tells us that the acceleration is decreasing. Acceleration is decreasing. Whenever say acceleration is decreasing, the velocity will be constant at a particular point where acceleration becomes zero. So we need to be aware of those points. Velocity is constant when acceleration becomes zero. Okay. So those are the basic of this graphs. Okay. Now, what information we are deciding the shape of the graph? The gradient, obviously. Based on the what the gradient represents, we can take different graphs and we can draw them. Then one more thing that we can draw is in the graph is the acceleration versus time graph. But I will give you an example of acceleration versus time graph. Let's say the object goes from 5 meter per second to 10 meter per second. Okay. In which graph represents correct motion? So in this, the four options were given. And the first option was to take an area under this curve for acceleration versus time. Okay, and the values were given like 0 to 10. Then there was option B, where they gave from 5 to 10 acceleration was something like this. Okay, from option C, it was clearly given something like this, where we have this as 10 and this is 1 and 3. And option D was given little bit shorter. This was 5 and this was 1 and 3. On the x-axis, there is time and on the options. So in this, which option seems correct? The correct option here is option D. Now, why is option D? Because area under the curve, area under A versus T graph represents change in velocity. And change in velocity we can find only for this graph. The area is 5 into 2, that is 10. And how much is the velocity changing? In the question given, it is 10 minus 5, that is 5 meter per second. So, so this is this way. This is 2, I think so, and then we will get 5. Yes. So it was option D like this. Okay. So every other graph do not satisfy because the area here will be 10 into 2, that is 20. Then here it will be 5 to 10, so that is 5 into 5, that is 25, and that will be divided by 2. So 12. Here the area is 12.5. Here the area 10, 10, 100 divided by 2 is 50. So it has to match the area, which is change in velocity, like this. So there are multiple scenarios where we can have to convert a given graph. For example, acceleration versus time graph was given something like this. Now we have to find the velocity versus time graph for this one. Now, how do we find the velocity versus time graph? So first we need to understand that the graph starts with the zero acceleration. Yeah, we have to look at different points. So this acceleration is zero. So graphs should have zero acceleration at starting and end points, and some maximum acceleration is also zero at the top. Correct? No, acceleration is non-zero at the top, but it is maximum at the top. Okay. So what should happen with the curve? The curve here should start with a zero acceleration, zero gradient. The gradient is zero. It means acceleration is zero, and it should have a maximum gradient here, max gradient, and then it will continue as a smooth curve, and it will have a acceleration that is zero again at the end. Okay, and since this is a curve, so it will go something like this. Okay, it can start from since this is positive acceleration, so it has to have a positive uh, gradient at the middle. So this is increasing and then it is decreasing. So here also there is increasing acceleration and decreasing acceleration. So gradient is also increasing, gradient is decreasing. Okay, so these are the same. So these kind of questions are expected to know. Also, one more thing that we can calculate is how to calculate instantaneous speed or average speed from the graph. So imagine if I have a graph of velocity versus time, okay, and my graph, let's say, gives me the curve something like this. So if I want to calculate average or average speed or average velocity or instantaneous velocity. So let's say at instantaneous velocity at p on the graph can be drawn by taking gradient or a tangent at point P. It will be gradient of tangent at P. So we will, if I take the gradient of the tangent, I will get the instantaneous velocity. Okay, but this has to be not a velocity versus time graph, but rather a displacement versus time graph. In displacement versus time graph, this will be very much clear. Okay. Then for average velocity, what we can do for average velocity? For average velocity, let's say at a particular point P, I will take the distance traveled up to or the displacement until point P. Okay, the displacement must be somewhere here. Okay, and then the time taken at. So the time at P. Okay, so we can take this and we can find the average time taken or average velocity from the graph of displacement versus time. Okay, so here the same things can be repeated if we have velocity versus time and we want average or instantaneous acceleration. The same technique can be used. Now we will try to draw the graphs of the examples that we did in the last video, where a person of car A was moving at a constant speed and reaches a particular distance. Okay, where a car B, who started from zero, accelerates and reaches the same distance in a given time where they both meet. Now, this example can be replicated or drawn in terms of graph, something like this. So if I have a velocity versus time graph, then for car A, it will have a constant speed. So it will have a horizontal line, while at a particular point, when we are drawing accelerated motion, then this is a car B, which has some zero velocity and then it accelerates. Okay. Now, when both of them, this is the time, let's say t, if they both meet at time t, then since the velocity versus time graph represents area, the area under car B curve till point t should be equal to area of car A till t. So the area has to be same, but they both must have covered the same distance by that time. So this is very small details, but these are the questions that can help us solve a particular problem if it is given in terms of graph. Okay. Then in another example where we thrown a ball upwards and then it lands, it goes to a certain velocity and then it comes down. This motion can also be depicted in terms of graph. Let's say if I have a velocity versus time graph, then this is very important to understand that the velocity at the maximum point is 0. Okay, so the motion will look like something like this. Now this is the point B. So if I differentiate this point A, there's a point B and point C on the graph, it will be point A, point B and point C like this. Now the point C is exactly the point where it's 0 at the top, and C, it has to be longer. The part C is longer because there is more displacement while coming down. There is more displacement. Okay, so it has to have a longer tail, and the velocity also is the higher in the negative direction. So here there is a major change in direction that is happening. Change in direction, and this is how we can reproduce a event in the terms of a graphs. Okay, in next video we'll look at some projectile problems and two-dimension, how to apply those equations. Okay, and some effects of air resistance on the projectile motion cell. So thank you so much.